Okay, thanks for having me. It's a pleasure to be here. Okay, there, I think I'm kind of in the picture there. It's a pleasure to be here. I'm very glad to talk to some people involved in formalization of mathematics here. My secret agenda for being here is recruiting. So I would be happy to have more people, well, not only for PhD students or something like that, but I mean for this project, the HoTTLean project. We would be happy to have more people involved in this project. And it's, of course, on GitHub. And you can send us a pull request and we'll be happy to work with you on that. And so that's one thing I want to say right up front is we're eager to have more collaborators. Good. Okay, so here's the HoTTLean, here's the homepage for the HoTTLean project. I show you this because it's on GitHub. So if you go looking for us, this is where you should go. And here are the names of the people who are involved in the project at the moment. This is Mario Carneiro, Sina Hazratpour, Joseph Hua, Wojtek Nawrocki, Shugaran, Spencer Wolfson, who's on hiatus maybe, and Yiming Zhu. And so if you go to the GitHub page, you will also find then our homepage on GitHub, which is the next, there we go. I wonder if I can zoom in, yes. And what I want to call attention to here is, yeah, this doesn't work. Oh yeah, down here, so there's a description here, and then here are some links to some recent papers about the project. So if you want to get more information about this project, you can look at these papers and they give details. They're from a couple of recent conferences and they give some details about different aspects of the project and give you kind of an overview. And then here's a nice little feature, how can I try it out? And you can see how far along we are. We're far enough along that we can have this feature on the GitHub page where you can kind of try out a prototype version of this thing. So, and now I'm just going to give you an overview of this HoTTLean project. So the subtitle there from the GitHub was Semantics of Hot and Lean. Maybe a more accurate subtitle would be a proof assistant for Hot based on Lean with an integrated translation of synthetic proofs into analytic ones. So I have to explain to you what that means. And that's kind of going to be the main part of the talk, is to explain what it means to translate synthetic into analytic. So first of all, let's start off by what is hot. Some of you probably already know, maybe all of you already know. I gave an overview talk a couple of weeks ago, which I don't expect you to have seen, but it's on the website of the Wednesday seminar series in the Computer Science and Technology department. And it gave the kind of big picture of the HOT project and some of the formalization stuff that's going on and the history of the project. But just very briefly, in a nutshell, HOT is homotopy type theory. It's a flavor of Martin-Löf dependent type theory, constructive type theory with pi types, sigma types, intentional identity types, some universes, and then some inductive types like the type of natural numbers and the sum types, and then the W types, which are a general type constructor for types of well-founded trees. Some various different inductive types can be given as W types. And then so that's kind of the basic part. And then there are some additions. There are what we call higher inductive types. These are inductive types which can be generated also by higher paths. And the higher paths, I'm not going to tell you a lot about them, but that has to do with the interpretation of the identity types. Identities in HOT are not just yes or no, true or false, Boolean values. They're paths, or they're homotopies, or they're higher homotopies, and so on, at least under the intended interpretation. And that involves lots of additional data, and that data can be put into the generating structure of an inductive type. So you can have an inductive type generated not only by the usual basic terms and operations and so on, like the natural numbers, but also by some higher identity paths. And those will give rise to some inductive types like, well, this quotient symbol is not just a usual quotient by an equivalence relation, but maybe it's a quotient by a higher equivalence relation, namely a groupoid. And then a quotient by a groupoid is a classifying space, or even higher equivalence relations like simplicial Kahn complexes and Siegel spaces. Or you could have something like the spheres, the higher spheres. The one sphere is just a inductive type generated by a point, the base point, and a single path which goes from the base point to the base point. So that looks like loop, like that. And then you take the inductive type generated by that, which means you can compose it with itself, you can reverse it and compose those and so on. And so you get something whose fundamental group is the integers. It's the homotopically the unit circle. And then there are the truncations, which are also inspired by or motivated by the homotopical interpretation, where you take a homotopy type of some space, and that may have all kinds of higher homotopy invariants, but you kill all those off and you truncate down to some lower level. And then, so those are the higher inductive. These things are all definable in type theory. It's quite remarkable as inductive types once you take into account the higher path structure that's naturally occurring in a type. And then the kind of essential feature or the big novelty is this univalence condition or axiom. Originally, we put it into the type theory as an axiom. It was inspired by the behavior of infinity topos theory with an object classifier, if that means something to you. The inventor was Vladimir Voevodsky, the celebrated homotopy theorist, and he arrived at this idea from his intuition about classifying spaces and moduli spaces of curves and so on, where a similar phenomenon occurs. And so some of these things are, I think I have the next slide. Yeah. So these first things are kind of standard Martin-Löf type theory. There, use the pointer, I guess. These are standard Martin-Löf type theory stuff. And then these are extensions that are not in the standard type theory, but they're compatible with it. And they're inspired by or motivated by this interpretation that I've already started hinting at, which is an interpretation of the basic intentional type theory into homotopy theory, or higher topos theory, infinity topos theory, where there are some things going on in there that are not just like extensional type theory in the category of sets. They're genuinely higher dimensional, and that inspires these extensions then of the type theory, which are trying to capture this higher dimensional structure and reason more effectively about it. And I say more about it in my CST talk, where these aspects of the type theory are there whether you like it or not. We're not putting them into this type theory, and the intentional identity types have this behavior, this higher dimensional infinity groupoid-like behavior. It's always been there. People just never noticed it. And then once we noticed it and started working with it, it became very helpful for using the type theory, which is a powerful and effective system to use because of its computational character, which I'm not going to say much about today. But that interpretation, which made the type theory more manageable, then we strengthened by adding some new conditions, which are not part of conventional Martin-Löf type theory. And that's these new ingredients, the inductive types and the univalence axiom, which I'll say a little bit more about later on. But for now, the basic idea is if you have two types, you can look at all the type of all equivalences between those types. And it turns out that that is or could be or should be the identity type on the universe between those two types. So if the two types, you take two types, they're in a universe, because that's how the type theory works. And then the universe has an identity type, and you can ask, what are the identities between those two types? Well, they're paths in the universe, according to what I already told you. And what's a path in the universe? Well, the univalence axiom tells you a path in the universe is an equivalence between the types, a homotopy equivalence. So it's a generalization of an isomorphism. Okay, so that's the basic idea of odd. Oh, so as a byproduct now, because we're using this constructive Martin-Löf type theory, which forms the basis of many proof assistants like ROC and AGDA and lean and so on, we can use those proof assistants now to reason via this, if you will, non-standard interpretation, or maybe now it's a perverse alternate standard interpretation, to reason about homotopy theory and homotopy types and higher categories and higher groupoids and so on. And we can formalize higher maths in these proof assistants, provided that we make the necessary modifications, like put in the univalence axiom and put in some higher inductive types and so on. We can use these proof assistants that you may be familiar with here in the formalization world to formalize results in higher homotopy theory. And that was one of the kind of red threads, leitmotif, what's the word, in my talk, which was about the formalization of the computation of the homotopy groups of the spheres. In the talk from a couple of weeks ago, I talked about the challenge of proving in HoTT and then formalizing and then actually computing the values of the third pi4 of S3, the fourth homotopy group of the 3 sphere. So that took about 10 years to finally get done. Recently, a big step forward has been the finiteness theorem, which computes all of the homotopy groups of all of the spheres and tells you that they're finitely presented and gives you the values. So there's a kind of big project going on of what we call synthetic homotopy theory, which is being formalized in, well, in this case, in cubical AGDA. I should go to my next slide and tell you about that. And then computing these values and using the formalization to compute the values. So previous implementations, the first one was Voivodsky, who I already mentioned, hacked what was then called Coq. He and Dan Grayson was the person I think was helping him with that. They hacked the Coq system in order to get the identity types out of prop and put them into type, if that means something to you. In the original Coq system, the identity formulas, A equals B, land in prop. Well, that's incompatible with HoTT. They have to be types and they have to be permitted to get bigger and bigger. And so there was a hack that allowed the identity type to go into type rather than prop. And then there were no higher inductive types in Voivodsky's original setup, but there was univalence as an axiom. Now, you might know that in Coq and in type theory, if you just put in an axiom, that's a stuck term. It's not going to normalize. It breaks the computational character and behavior of Coq. So one of the advantages of Martin-Löf type theory is its computational character. And so it was an open question and a challenge whether one could integrate into the system the univalence axiom, and maybe as a principle or as a rule or something like that. And in subsequent libraries, like the ones I mentioned, people were experimenting with different approaches. So there's a parallel development of HoTT in the Coq ROC system, which does include higher inductive types and allows you to use that system to compute some homotopy groups of spheres. That was developed largely by Andre Bauer and then Mike Schulman. They did some early calculations in synthetic homotopy theory. Then there's the AGDA system, which you can hack by getting rid of the sets effectively. But if you use the flag without K in AGDA, that permits you to have higher types of data. And then there's AGDA Unimeth, which is a nice development. It has hits, it has univalence and so on. Egbert Reike has been the main developer of that. If you search for that online, you'll find a very nicely organized AGDA library with all kinds of results in synthetic homotopy theory. That's Egbert's project. Let me recommend, while we're at it, Egbert's new book, published by Cambridge University Press, Introduction to Homotopy Type Theory. It's just out in the last couple of months. It's also, I think, in some preliminary version online and maybe on the archive. But hey, go buy it. And then all of the material in that is formalized in the AGDA Unimeth library, and that makes a really nice learning tool if you want to learn HOT and formalization, you read Egbert's book and you learn Agda at the same time, and it's all there. So that's a nice setup. The thing that I talked about in my talk, this challenge to make univalence compute, that was finally solved after 10 years of hard research by Thierry Cocon and his collaborators, including Anders Mortberg, Swedish people, and others, who developed a variant of Agda called cubical Agda, which incorporates some hits and notably univalence and still computes. It was proven by John Sterling, who's now here in the computer science department, that this thing has the canonicity property. So it will have normal forms and it will compute. So you can compute values. If you formalize some synthetic homotopy theory in cubical Agda, you can use univalence, you can use hits to get the spheres. And then when you compute, and then when you prove in cubical Agda that pi4 of S3 is Z mod n for some term n of type nat, you can hit return and it'll normalize that term n and it'll compute the value 2. So you can, from the proof term for the proof, you can compute in cubical Agda the values of the numbers involved. So cubical Agda is a big breakthrough. And then there have been developments in Lean, and that's what we're interested in today. Let me kind of move on. In Lean 2, there was a hot mode in Lean 2. Leo de Moira was generous enough to incorporate a switch into the early version of Lean that allowed us to do hot. It basically did what the hack in Coq did, namely it put the equality types into type rather than prop. And it allowed us to do hot. And we built a whole hot library, and there was a lot of work done in there. At the time, a PhD student at CMU was, I should be in the camera, should I? Was Floris van Doorn, who's now a professor of formalization at the University of Bonn. And he built this hot library, not single-handedly, but he did a lot of the work, and he formalized the Serre spectral sequence as his dissertation in Lean 2. And that was quite an accomplishment. Notably, Lean 2 had an impredicative universe, and I don't mean a universe of propositions, I mean a universe of types that was impredicative. So it was compatible with, if you're familiar with Girard-style System F impredicative encodings of type constructors, we did some of those in Lean 2 using the impredicative universe of types. So that's quite fascinating. Then Leo moved on because Lean is a moving target, as you Lean people know. And then Lean 3 didn't have the hot library. Then people built a new hot library in Lean 3 using a different hack. And then they got about halfway through that, and then Lean 4. And now people are kind of losing steam, trying to keep up with Lean. And so there hasn't been a hot project in Lean for some time, and that's where we are now. Is we're trying to build a new hot project in Lean, but we're not using, for reasons that I'll tell you in a minute, just the old hack of putting the equality types into type rather than prop, largely for reasons that I'm going to explain in a minute, but because Lean has so much infrastructure and has mathlib and it has all of these tools, and they're not compatible with that hack. So we're not doing that anymore. We have a different approach, which I'm going to tell you about now. But first, let me just say very quickly, why do you want to do hot in Lean? Just leave it alone. Why don't you do hot in cubical Agda? That works great, right? So why bother? I mean, Lean has made it clear that they don't want us. So why are we chasing them, right? It's like a spurned lover and you won't pursue. Well, for one thing, it would be a way of providing in Lean access to some higher math, homotopy types, infinity groupoids, infinity categories, and so on, using the synthetic approach of HOT. So we could use Lean to formalize results in homotopy theory directly without developing the whole theory of simplicial sets and geometric realizations and all that machinery. HoTT is a kind of royal road to homotopy theory. Does that make sense to you? The Germans have the expression in the Königsweg. It's like a shortcut to homotopy theory because it has this synthetic approach where you don't have to do the simplicial sets and the geometric realization and all that stuff. You just kind of use the type theory, I think I say it later on, as a domain-specific language for homotopy theory without building all of that analytic infrastructure. So that's one reason it would be nice to have HoTT in Lean, because then in Lean you would have access to those cool methods. Another reason would be you would have univalence in Lean, which you don't have now. And univalence is very convenient, even for everyday high school algebra. It's convenient to have univalence because univalence, as I said, it identifies isomorphic things. It allows you to do group theory without fooling around with equivalence classes of elements to make a quotient and swapping out different equivalence relations. You can just identify isomorphic things the way you do in everyday modern mathematics, right? Whereas in formalization, there's a lot of fussing around that goes with isomorphism and keeping track of the structure of isomorphisms and so on. You can make use of what's called the structure identity principle, which already works for algebraic structures and allows you to identify isomorphic structures. So those are two reasons why you might want to have HoTT in Lean or some aspects of HoTT in Lean. From the other point of view, from the HoTT point of view, we would like to make use of some of Lean's features, some of Lean's infrastructure, some of Lean's user interface. The MATLib library is very comprehensive now. And so there are lots of nice tools in Lean, the Lean tactics, all the great infrastructure that's been built up. Lean is like a big snowball now, and it's rolling down the hill, and it's gaining steam, and it's gaining mass and users. And as HoTT users, we want to get on that train as it leaves the station. We don't want to be left behind. So that's another reason. We want to make use of MATLib and some of the results in MATLib in our HoTT formalizations. So that would be nice too, to be able to do HoTT in Lean. And finally, we have this idea in the HoTTLean project that maybe we could do synthetic proofs in HoTT, and then, like you do in computing homotopy groups of spheres, push a button and decode them into analytic proofs. That would be really cool if we could decode a synthetic proof into an analytic one, which we then push to MATLib, and we use our secret methods to contribute to MATLib. Yeah.
Can you clarify exactly what you mean by the distinction between synthetic and analytic?
I know I'm being a little fast and loose with that.
Okay.
But roughly speaking, and I think I say more about it later on, is that let's say you have a kind of axiomatic description of some mathematical structures, and then you have examples of building them up from below, from sets and so on, like when you use simplicial sets to model homotopy types, or when you use some ordinal numbers to model types of ordinals, or sets to model some specific sets to model well orderings, things like that. So the axiomatic description is what we call synthetic, where you work in the type theory, the types and terms implicitly, but not explicitly, denote some mathematical objects that you don't have to unpack. And then an analytic description would be the unpacking into explicitly constructed instances of the axiomatic description. So that's I don't know, the synthetic analytic is just something we came up with as a way of describing maybe axiomatic versus concrete is a better, more familiar way of putting it, but it seems to have caught on, and I've heard other people using that terminology now. So that's the idea. Okay, so see, so why can't we just use cold Lean to do HoTT in Lean, right? I told you before, it has to do with the equality types in the way that they're implemented in Lean. So first of all, there's extensional Martin-Löf type theory, which has this reflection rule. I'm writing this for the equality type, that's a type. And then this is the definitional or judgmental equality in the type theory. I hope you're familiar with Martin-Löf type theory and the difference between a propositional and a definitional equality, or a judgmental versus a typal equality. But this is a judgment. You can't, it's not a type, and you can't build new types with that in it. But this is a type which represents equality, and it can be part of a big complex type. And in Martin-Löf's extensional type theory, which he abandoned in the 80s because it's not strongly normalizing or decidable or anything like that, in that system, you have this reflection principle. If you have a propositional equality, a proof of that, you can reflect it down to a definitional equality, and then you can swap X for Y everywhere it occurs anywhere else. That's called proof irrelevance, definitional proof irrelevance. Then there's kind of a milder form of proof irrelevance, which says, if you can prove a propositional equality between X and Y, then, and you have some other proof, then those two proofs are propositionally equal too. There will be some alpha here maybe which proves that P and Q are propositionally equal. That's a kind of proof irrelevance in the sense that any two proofs are equal if they're proofs of an equality type, or I say identity type because that's the Martin-Löf terminology, but it's maybe equality type is better for extension. So that is like the basic setup in the old calc proof assistant, where the type prop is proof irrelevant, but not definitionally so. Question?
I think there's a question in the chat by Joseph. So
okay.
So you'd like to read Joseph? No.
Joseph, can you just put it in the chat, or can I turn him on or something?
Yeah, no. Yes.
I just wanted to, you've clarified the thing that I was going to say.
Okay.
It's okay.
Okay, good. Well, you're going to have more to say when I get further down the slide, because I'm playing fast and loose with some of these explanations in order to get it through the talk, because I'm using the kind of author's license here to give a streamlined version of technical things that are actually more subtle. So the next thing that I'm being a little bit sloppy about is definitional proof irrelevance in Lean. In Lean, what you have is proof irrelevance in this sense, but then you have a definitional reflection for these proofs. So if P and Q prove some two terms are equal in the sense of a propositional identity type, then P and Q are definitionally equal. So it's kind of like a combination of these two things, but the reflection only happens for terms of this higher identity type. That's approximately the situation in Lean. Lean users might object now, but I'm going to push on. Then there's basic Martin-Löf type theory, which you can find in AGDA with the flag without K turned on. And that gives you proofs of identities, identity types, and those out of those you can build higher identity types, which may or may not be inhabited. It may be that they're not inhabited. And then you have two different proofs of a propositional equality. Or it may be that there are proofs of P equals Q, and there may be several of them. And those in turn may be identified, those proofs, or not, or identified in multiple different ways. And this is what leads to the hot idea that we should stop trying to force equality to be proof irrelevant, propositionally proof irrelevant, higher proof irrelevant. Let's let equality be. Let equality be free. Maybe there's a slogan here, right? Because by free, I mean you can multiply equality proofs ad infinitum. That's what the ... is. So free equality. There's a bumper sticker here somewhere. So you can have so the idea is you can have two terms and they can be equal in many different ways, and those equalities can be equal in many different ways, which in turn can be equal or not in many different ways, and so on. And that's what leads, and the fact that these equality proofs can be inverted by the symmetry law, composed by the transitivity law, and satisfy higher laws like associativity and to interchange law and all kinds of laws from higher category theory, that leads to this very fascinating, complex, higher dimensional structure on every type that's endowed with by the tower of identity types in the intentional Martin-Löf type theory. Okay, so that's a very quick reason we want that, right? We don't want to kill that. And that's why HoTTLean is not going to work. Okay, so another problem with using HoTTLean is Lean bakes in classical logic and with the Hilbert epsilon operator and the axiom of choice. And nowadays, more and more, MATLib bakes in classical logic. It's used extensively to speed up proofs. Classical logic is great if you're in a hurry, right? And so it's shot through, MATLib is shot through with uses of classical logic and the axiom of choice and non-constructive reasoning and so on. That's unfortunately incompatible with univalence. We want univalence. We don't want everything to collapse. And so if you want to have higher types with higher homotopy groupoids or higher structure of identity types, the universe of all types looks like this. You have like the universe is going up in Lean, or in set theory or whatever, you're familiar with this hierarchy of universes, but there's a second independent dimension of what are called the homotopy levels of structure. So this is prop down here. This is the universe of sets. This is the universe of one types, the groupoids, two types of two groupoids, and so on. This goes on without end, and it's independent of the dimension of size. So there's a whole plane of types in homotopy type theory of not only cardinal size, but also homotopical dimension. But in Lean, everything is baked down, pushed down into either prop or set, and the higher cardinals. So we can't use cold Lean for that reason, you know. So we want to have these higher types. That's the distinctive feature of HoTT. Okay, so how are we going to do it? So here's the approach that we're using in this HoTTLean project now. We're going to formalize in Lean a model of HoTT, the whole thing, not just the type of some structures or something, but the whole model. And the model we start with is kind of the most, or maybe the first non-trivial model. It's not just sets. That's the model of extensional type theory. It's the model in groupoids, and I'll tell you a little bit about that. It was invented by Martin Hoffmann and Thomas Streicher 20 years ago. And it's a model of HoTT built out of classical mathematics, algebraic structures, groupoids, which are a kind of generalization of a group. And you can build it in MATLib. And a lot of the ingredients for this model are already in MATLib. And some of the other ones that you need, we're pushing into MATLib now. Then we take HoTT and we translate the types in terms of HoTT into that model. And we use Lean to reason about the translation. So that's the idea. So one, in the kind of parlance of the current jargon, this is a deep embedding of HoTT into Lean. It uses HoTT as a domain-specific language, maybe, to reason about the groupoid model. So maybe that is a way of explaining what we're doing. And then the HoTT proofs, which can involve synthetic methods, by which I mean axiomatic proofs in intentional type theory with univalence and higher inductive types, can be translated or compiled down or something to yield analytic results about the model, which are formalized in MATLib, in the groupoid model in MATLib. So you prove something in HoTT, and then you can unwind the axiomatic description in terms of the model, and you end up with some statement about some algebraic structures which can be formalized in MATLib or can be verified in Lean. So that's the idea, maybe the big picture. And then here's the picture of the big picture. At the top we have, so I think there's nothing there, okay. At the top we have this, what the user sees is something that we're calling SynthLean. It's an interactive proof assistant for doing synthetic mathematics in Lean and checking proofs in this language of HoTT, which also incorporates univalence and higher inductive types and so on in principle. And then this layer, and now this part is kind of under the hood, if you will, this SynthLean checks proofs in a system that we're calling HoTT0. It's a fragment of HoTT that has a univalent universe. So that's an extension of Lean. And the univalent universe is the universe of all sets. All the kind of basic, familiar, discrete types of HoTT that behave like sets. And that has univalence. And then that fragment of type theory, so it's not all of HoTT, it's just part of HoTT, this HoTT0. And that fragment then is interpreted formally into some abstract semantics described using axiomatic category theory. I mean, you could jump straight to the model in groupoids, but it's useful to mediate by using an axiomatic description of the model into which the type theory interprets. So there's a kind of articulation of the interpretation into two steps, which not only makes the project modular and easier to manage, but for reasons that I'll tell you later, are also practically convenient. So the first step of the interpretation of this type theory is to interpret it into an abstract description of a model of type theory. And then there's an instance, a specific instance of that in the groupoid model. So the groupoid model is just concrete algebraic structures like you know from high school algebra, or if you had a good high school, or MathLib or whatever. That's the concrete model. And then there's an axiomatic description of it using some abstract category theory, and then the interpretation of the type theory into the categorical or abstract model, and then the proof checker in SynthLean, which interprets proofs in HoTT into this abstract, into this type theory. Okay, and so now for the rest of the talk, yep.
So there's a question in the chat. By
Oh, good.
So,
Who's the question?
Paul Taylor.
Paul Taylor.
Yeah.
Okay, well, hi, Paul.
Yeah, so Paul asks, are you saying that the interpretation of a HoTT proof of a statement in homotopy theory in the Hoffman-Streaker model is the traditional homotopy theory?
I don't get it. It's too much. The
Yeah.
interpretation of a
Yeah,
statement in HoTT0, which is a type theory,
yeah.
in the groupoid model
Yeah.
is a statement about groupoids. So I don't know what.
Right. Yeah. So the question is like, are you saying that the interpretation of a HoTT proof of a statement in homotopy theory
Yes.
in the Hoffman-Streaker model is the traditional theory?
No, I'm not saying that. The model is an analytic model of the homotopy types are classified by groupoids, but statements in homotopy theory are not the same thing when you interpret them into groupoids as the homotopical statements. They're statements about groupoids. So maybe that answers the question. We can discuss it more later. Yeah.
So if the user up there wants
Yeah.
to see the result of a computation,
Yes.
don't you have to go backwards now from the
Yes.
bottom to the top?
Yes.
Okay.
And so that's, yeah. And so that's an interesting task, is this kind of back and forth, like
Yeah.
how much of this layer is visible to the user?
Yeah.
Or is there a way of producing that or having the two things interact with each other, maybe kind of going back and forth? Because ideally, if what you're trying to do is produce results down here, classical results, you might want to know what's going on and have some feedback or back and forth. And so that's part of the engineering problem of developing this layer to permit that. And now I'm going to go through these 1, 2, 3, 4 layers one at a time, and the rest of the talk and tell you about them. And that first one, which is a very interesting one, I'm not going to say anything more about. That's next week. So that's a big subject. Wojtek is the one who's been driving that largely. It uses Lean's meta-programming feature to build this kind of interactive proof assistant for HoTT0 in Lean. And all the other layers too. So Wojciech is going to tell you next week about some of the details of how this coding goes. Okay, so now the next step was HoTT0. What is that? It's a kind of Martin-Löf type theory. Now we only have finitely many universes because you have to cut it off somewhere. You can't have the whole thing, otherwise it would be not compatible with Lean. So we have finitely many universes. Each of the universes has the familiar type formers that we know about, sigma, pi, and id. For now means we might add more stuff later. This is just where we're at right now. We'd like to have some quotients and some other type formers. Then there are some axioms for HoTTLean. Globally, we need to add function extensionality because that's not part of Martin-Löf's intentional type theory. It's implied by univalence, which is a remarkable result, but we only have univalence for one universe, not for the whole thing. So we have to put that in as an axiom, and then we put in univalence for each of the sub-universes of sets in these finitely many universes, right? This is the kind of the two-dimensional structure that I was talking about. We're in one column of my chart of the plane of types, and for the column that has the second column in of sets, that's where the univalence lives. And the reason is that univalence is a statement that's formulated in the next universe up. So to talk about univalence, you need a next universe up to state the univalence condition. Okay, so we put that in as axioms. And then this implies, for example, the structure identity principle that I mentioned for algebraic structures. Like if you have two groups, regular old groups with a structure on a set, and the groups are isomorphic, it implies that those two groups are identical in the sense of the identity type on the type of all groups. So that's the special case of univalence for algebraic structures, set-based algebraic structures. So that's a fragment of HoTTLean. Okay. The next step was the axiomatic semantics in abstract category theory. I'm not going to say a lot about it. I'll just very briefly sketch what's involved. And then when I do the groupoid model, I'll give you an example, and that will hopefully make this a little bit more clear. But the basic, and this is some kind of category theory that's being formalized independently. Like I said, the project is modular. And so this is stuff that will be pushed into MathLib and can be used for other purposes and so on. So it's presheaf categories where we have the contexts of the type theory are abstracted by a category, which we think of as the category of context and substitutions. And then in the category of presheaves, we have a notion of natural transformation. And so we take a specific natural transformation here, which takes the presheaf of types in a given context. That's a presheaf because it respects substitution. The presheaf of terms, and then the typing operation of a term that takes a term to its type turns out to be a natural transformation between those two presheaves. Here's a picture of it right here. And then, so maybe I skipped to this. The semantics is formalized like this. If I have a context and in that context, a term of this type, then the context gets represented as a representable presheaf, and a natural transformation into the type of all types is exactly a type in that context. So the interpretation of gamma turnstiles big A is a natural transformation, and a little a, which is a term of that type in that context, is a lift across this typing natural transformation. So that gives a very easy to use natural, pardon the pun, semantics for types and terms in the category of presheaves. And then this particular kind of universal family of terms over the types can be used to build in the categorical sense a polynomial endofunctor, which is a thing that looks like this. And that's a nice kind of well understood categorical structure that lives in any locally Cartesian closed category like this. And we use those polynomial endofunctors now to give a kind of very clean algebraic semantics for dependent type theory. That's part of the recent contribution of this project is, you know, I'm sure you all know when you do formalization, you have to kind of rethink things and how they work and arrive at good descriptions of the structures. And one of the things that we've arrived at is very clean algebraic semantics for dependent type theory, involving polynomial functors and the type formers, like, for example, the pi and its associated term former, the lambda abstraction, can be described as simple pullback squares between this universal family and its image under the polynomial functor that it produces. So that's one of the kind of type formers, and the other type formers have similarly concise algebraic descriptions. So all of that stuff gets formalized in Lean and pushed into MathLib to some extent, and then used for this layer of the HoTTLean project. And this is, for the most part, done. So then there's the groupoid model, which will be an example. So the category of contexts and substitutions is the category of groupoids. So contexts are represented as groupoids, and substitutions, terms, telescopes of terms between the contexts are represented as groupoid homomorphisms. So that's the basic algebraic instantiation of that abstract semantics. There's a universal family of types, which turns out to be in the category of groupoids, the category of all pointed groupoids. This is a groupoid with a distinguished object, and a homomorphism is a groupoid homomorphism that takes the object to the object on the other side, maybe with an isomorphism between them. And then there's a forgetful functor to groupoids, and that, it turns out, is the universal family in our model. Now, what's happened here, maybe you noticed that that thing can't also be in the same category as the category of groupoids. So I'm moving to big groupoids, large groupoids, class size groupoids, so that this can be an object. That's a kind of a fine point, but it makes use of Lean's universe management. And it turns out that there's quite a bit of interesting and subtle care that needs to be taken in using the universes in Lean to formalize this in the project. So then there are the dependent types and terms, which I just explained. They're modeled like this, where this is a groupoid, and this is now a functor from the category, from the individual groupoid interpreting gamma into the groupoid of all groupoids. That's a dependent type. And then a dependent term is a lift of the functor into the pointed groupoids. Substitution, of course, is modeled, as I told you, by a homomorphism. And so this interpretation of a type in context gamma and a term in context gamma, if I substitute in, I just compose to get the interpretation of substitution, and that will satisfy the rule that says a substitution into a substituted type is a substitution of a substituted term into that type. And it gives us the coherence or the strictness of the interpretation of substitution of terms into types, which traditionally has been a big problem in the interpretation of dependent type theory. So in this interpretation with a universal family, homing in gives a coherent interpretation of the dependent types. Yes.
So Andrew raises hand on the
Who is it?
Andrew Pitts.
Oh, Andy Pitts. Okay, great. What does he have to say?
Hi, Steve.
Speak for
Hi.
himself?
Hi.
Hi.
Could you just back up a slide?
Oh, sure. A whole slide. That one or more back?
No, another one. Another one. Yeah, great, cool. So, strictly speaking, natural model semantics is some mathematics in which you can give the semantics of type theory. It's not actually the semantics. So I haven't seen Wojtek's talk yet, so I don't know what the syntax of the top layer looks like exactly, but I guess you've formalized the semantics of that top layer in a natural model, right?
Yeah.
Now, the traditional way of doing that, it's not that nice, right? I mean, Hofmann and Stryker use sort of partial elements and then prove totality and so on.
Exactly.
Do you do that? And did you
Yes.
find there were any difficulties?
Wojtek should tell you about that, but yes, we do. The interpretation is a partial interpretation, and then you have to choose. You have to prove that it's total on the well-typed terms.
And moreover, you're forced not to use the syntax that you wanted in the first place, but you have to put in a lot of explicit type information, annotation.
Yeah, there's a
Is
lot
is that true for you, or have you found
Yes.
some cool way of getting around that?
In fact, we just discussed that yesterday, that's leading to performance issues when you actually.
I'm not surprised.
Right.
Yeah.
When you actually get this thing to, we recently had somebody finally formalized an instance of the structure identity principle, the univalence for the type of what are they called, magmas, right? The most simple algebraic structure, and checking it took 5 hours.
After Peter Axel, we kind of know that you can get around that in certain cases, namely the set theoretic semantics. I think it's an interesting research topic to try and get around that problem because it's actually practically very annoying.
It's going to be, once we get anything to work, even if it takes 5 hours, then optimization and performance and efficiency and so on are going to be the next things. And they are, of course, as you know, related to interesting mathematical problems as well. So that's going to be kind of the next phase. But first, we're just trying to get anything to work.
My money would be, my bet would be on directly giving a meaning to the proofs of the judgments in the top layer and then proving irrelevance of proof irrelevance.
Yeah, that's one of the things that Wojtek mentioned yesterday, in fact, in our meeting. So save that question for next week and he'll have something to say. We considered going on derivation trees rather than terms. There's a trade-off there, so forth. So
if you're like me, you'll find there are subtle and interesting problems with the recursive definition, but never mind.
Okay, good. So yeah, those are interesting technical and also mathematical and also engineering questions involved in this project. Okay, let me speed up here because I'm kind of almost done, but I think there's some other stuff I want to tell you about. Oh, I seem to have lost my connection. Maybe I do just use this. There we go. I wonder why that stopped working. Anyway, so I'm telling you about the groupoid model. It looks like this. I don't know why it stopped working. No, that's okay. I don't want to bother with it. We're kind of done. Here's the groupoid model. Oh, here was context extension. I didn't tell you much about that. Context extension is modeled by pullback of the universal family, which turns out to be the Grothendieck construction, if you've ever seen that before. So that's an interesting thing that was missing in MathLib. We had to do that, and we've pushed that into MathLib. I don't think it's been pulled in yet, but anyway. And then there are the type formers, the sigma and the pi, and so on. They end up getting interpreted in the usual way by left and right adjoints to pullbacks in the model, that is. I mean, there's also this polynomial description, but this is maybe the boiled down version of it. And that uses the Poly project, which Sina Hazratpour, who is here, started and has been managing and is leading now. And that is interesting. As I said, the project is kind of modular, and one of the modules is the Poly project, which formalizes in Lean the theory of polynomial functors, and that has other applications too. So we make use of that. We build on the Poly project to do this aspect of the HoTTLean project. Okay, so maybe Sina will give us a talk about the Poly project at some point. So finally, in the groupoid model, what are the identity types? Well, just very briefly, an identity type in the groupoid model, one of the nice things about it is this description of the identity type as the arrow groupoid. If this is just a type, forget about the gamma, the context, think of it as a closed type, then this is A cross A, and this is the groupoid of isomorphisms in the groupoid A. It's another groupoid. That's the interpretation of the identity type. The identities between two objects in a groupoid are the arrows in the groupoid. So the arrow groupoid models the identity type, and there could be more than one. So that's the kind of proof relevance. On the universe of all sets, the identity type between two sets is, according to this recipe, the arrow groupoid of sets. It's all the isomorphisms between those sets, because sets here is acting as a groupoid. It's a groupoid of sets and isomorphisms, sets and bijections. That's the arrow groupoid. But hey, that's just the type of all isos between those two sets, A and B, which is a type theoretic construction involving sigma and pi and identity types and so on. So here is the univalence axiom instantiated in groupoids and being true. So this is univalence, right? This is identity between A and B in the universe of all sets. And here is the isomorphisms between A and B, which is what equivalence means if these things are sets. And here are those two types being equivalent. I wrote it as equals, but you should say they're equivalent. And that's the univalence axiom. And the univalence axiom, it doesn't have to be an axiom in this model. It's just true. So univalence is true in this model in the category of groupoids. So that's why we like to use that. Okay, finally, what can you do in HoTTLean? Let me wrap it up quickly. Well, as I said, you can do some synthetic topology. You can't do a lot because we only have 0 types and 1 types, but you can do some. So you can do classifying spaces for groups. This is what I told you before, the quotient by a group structure. You can do the theory of torsors and bundles, covering spaces, the classical algebraic topology. If you read the first chapter of Hatcher's book, it does the theory of covering spaces and the actions of the fundamental groupoid or fundamental group on covering spaces. All that stuff is doable now in this truncated version of HoT in HoTTLean. I mean, that's been done in HoT, but we can do it in Lean now. We can do some synthetic group theory, as in the symmetry book of Buchholz and others. They're doing a very interesting approach to group theory in HoT in a synthetic style, where groups are represented by pointed connected one types. And we can do a lot of that stuff already in this fragment of HoT that's available in HoTTLean. As I already explained, we have the structure identity principle for algebraic structures, which simplifies some results in algebra. It definitely simplifies category theory. It simplifies some sheaf theory where you have patching conditions on sheaves of algebraic structures. That's something that I think Kevin Buzzard was proposing as a challenge some years ago. The definition of a scheme. The definition of a scheme has been effectively done using HoT in cubical agda. So that's simplified. All the patching conditions for a sheaf of algebraic structures are simplified in this setting. And in fact, all of MathLib's classical set level math in principle lies within the universe of sets in HoT0, right? I mean, we haven't ported that all in, but one could start trying to do that because Lean is a fragment of HoT0. HoT0 is an extension of Lean. It has a subsystem of just sets, which can be just the classical sets of MathLib. So we can think of this project as an extension of Lean by adding higher types and then adding these principles. And finally, the whole setup is modular, as I've emphasized. And so the different modules can be swapped out. And in particular, we could go from groupoids to 2 groupoids, to n groupoids, to infinity groupoids. And we could use the model in con-complexes rather than the model in groupoids in order to do full HoT, the infinity groupoids. And we can do kind of higher extensions of the HoTTLean project to the level of the models of infinity toposes or full book HoT that we know of in everyday HoT stuff. So that's the kind of long range. There's no end to the interesting work that can be done. So that's it. And then next week, Wojtek will tell us some more. Okay, thanks for your attention. Sorry for going over it. Any questions online?
Yeah.
Yeah. Should we just let them speak or?
Yeah.
Okay, okay, go ahead. If they want to. Can I, what do I have to do? Do I have to do something? Here's the chat. We could, oh my goodness, there's all kinds of stuff in the chat. What do we do?
So if anyone has any questions online, feel free to unmute and ask.
Yeah, if I hi
So
Steve.
the answer to Andy's question is yes, they do show Fox News all day. It's just like at the airport in the United States where Fox News is on all day at the airport. And don't ask me why. And then the answer to Paul Taylor, we already had. Joseph had, I think we already covered that. Wojtek is here. Wojtek says we do the classical, or maybe he's going to say it himself. Wojtek, are you there? Oh,
Hi, I was just answering Andy's question, but I think it's now.
Yeah, so classical partial interpretation. Yes, the syntax is indeed fully annotated. So that's the answer to Andy's question that we already had. Somebody has to go. Thank you very much. You're welcome. Thank you. You're welcome. Cubical type theory and con composition. No, we don't have plans for that because that's what Cubical Agda does, and it does it well. I don't think well, maybe somebody will want to do it. I don't know. At this point, we don't have plans for that. And then here's another question. Are there any good first issues you could recommend? Yes. Someone familiar with BookHot and reasonably skilled at Lean. Yes, get in touch with me soon and we'll set you up. Maybe you are on the Lean Zulip if you're already reasonably skilled at Lean. There's a HoTTLean channel on the Zulip. Introduce yourself there and we can continue our discussion then. But yes,
Right, cool.
There are lots of
Thanks.
good projects. Lots of good projects. So jump on the HoTTLean channel on the Zulip and we'll talk about it. Wojtek has already given you a pointer to it in the chat, and he's probably ready with some tasks that he needs people to work on. So issue tracker, there it is. There's an issue tracker on the GitHub page for the HoTTLean project with lots of issues. Okay, that's a good answer. Thank you, Wojtek. That's the right answer. Okay. Anybody here have any questions?
Any other questions?
Maybe we kill the Zoom. Oh, go ahead. Yeah.
Oh yeah. Sort of a quick one. Maybe this is a question for SynthLean, but I was wondering how the terms in HoTTLean are constructed. Like, are there, for example, like, are there tactics that allow other tactics that means more convenient, like, or is it like? Or are there plans for it? Or so like, I was wondering how this works.
The idea is, I mean, Wojtek will tell you more next week about that part, but the idea is that one should be able to use lean tactics as well.
Okay.
That's the goal. I mean, otherwise you could just start from scratch and make a new hot proof assistant.
Yeah.
The reason for doing it in lean is we want to use lean's infrastructure too. So.
Okay.
Yeah. Okay.